Dear students, today we have learned fluorometric analysis. In this contains are introduction, theory, molecular structure and fluorescence. Firstly, we have seen introduction of fluorometric analysis. It is also called as fluorometry and phosphorometry. A large number of substances are known which can absorb ultraviolet or visible light energy. But these substances lose excess energy as heat through collisions with neighboring atoms or molecules. However, a number of important substances are also known which lose only part of this excess energy as heat and emit the remaining energy as electromagnetic radiation of a wavelength longer than that absorbed. This process of emitting radiations is collectively known as luminescence. In luminescence, light is produced at low temperatures. Therefore, the light produced by this process is regarded as light without heat or cold light. Luminescence is of two types. First one is fluorescence and second one is phosphorescence. Firstly, we have seen fluorescence. When a beam of light is incident on certain substances, they emit visible light or radiations. This phenomena is known as fluorescence, and substances showing this phenomena are known as fluorescent substances. The phenomenon of fluorescence is instantaneous and starts immediately after the absorption of light and stops as soon as the incident light is cut off. Second type of luminescence is phosphorescence. When light radiation is incident on certain substances, they emit light continuously even after the incident light is cut off. This type of delayed fluorescence is called phosphorescence, and the substances are called as phosphorescent substances. Materials exhibiting fluorescence generally re-emit excess radiation within 10 raised to power minus 6 to 10 raised to power minus 4 seconds of absorption. On the other hand, materials exhibiting phosphorescence re-emit excess radiation within 10 raised to power minus 1 to 10 to 20 seconds or longer. Thus, the lifetime of phosphorescence is much longer than fluorescence. So, we have seen now comparison of absorption and fluorescence methods. Ultraviolet and visible spectrophotometers and fluorometers should be considered not as competing but as complementary instruments due to the fact that relatively few compounds fluorescence an extremely valuable tool as a selective analytical process is available. The determination of fluorescent compounds in the presence of non-fluorescent compounds is very simple. It is often unnecessary to subject the sample to preliminary procedures in order to remove absorbing interferences. They are simply zeroed out on the instrument. Several system features supply a versatility in fluorescence and that is not available in absorption methods. In molecular fluorescence, wavelength choices in both the absorption and emission wavelengths are available for use. Interferences may be avoided in fluorescence procedures by utilizing wavelengths at other than the maxima. In spectrophotometric absorption procedures, serious errors result from the use of either the rapidly rising or falling portions of a spectrum, or sensitivity may be lost by using the minima of the curves. No such restrictions are faced in fluorescence analysis. Fluorescent data are not subject to the relative error curve since intensities are direct and linear measurements, whereas absorption readings are indirect and exponential. The precision and accuracy of a fluorescent procedure are constant over the entire instrument range. Now we have seen theory of fluorometric analysis, singlet and triplet states. In order to understand the theory of fluorescence and phosphorescence, one has to understand the meaning of singlet and triplet states. These terms arise from multiplicity, absence of a magnetic field, sorry, from multiplicity, consideration of atomic spectroscopy, and simply define the number of unpaired electrons in the absence of magnetic field. Most of the molecules in their ground state do not have unpaired electrons, means singlet state. When such a molecule absorbs ultraviolet or visible radiations of the proper frequency, one or more of the paired electrons, generally a pi electrons, get raised to an excited singlet state. In this excited state, the spin of the electron does not undergo any change and the net spin is still 0. One more possibility is that one set of electron spins may have undergone unpairing, resulting in two unpaired electrons which make an excited triplet state. Now we have seen excited state process in molecules. When molecules are irradiated with light of the appropriate frequency, it will be absorbed in about 10 to the power minus 15 seconds. In process of absorption, the molecules may move from the ground to the first excited singlet electronic state. Although at room temperature molecules may be present in their ground vibration level, after absorption the excitational molecules can end up in any one of the vibrational levels in the first excited electronic state. From the excited singlet state, one of the following three phenomena will probably occur depending on the molecule involved and the conditions. First phenomena, the first possibility is that the excited singlet state is relatively unstable. In such a situation, the excited molecules will return to the ground state by collision deactivation without emitting any radiation. And the second possibility is that the molecule in the excited singlet state may emit an ultraviolet or visible light photon. This process is known as fluorescence. If we compare the absorption and fluorescence spectrum of the same compound, they do not superimpose on each other as expected, but they are mirror images of each other with the fluorescence spectrum shifted to longer wavelengths. The reason for this is that as the time required to execute a vibration of about 10 to the power minus 13 seconds, which is much shorter than the decay or mean life of 10 to the power minus 9 seconds. Most of the excess vibrational energy will be given to the surroundings and then the excited molecules will decay in their ground vibrational levels. This is illustrated in Jablonski diagram. And the third possibility is that the molecule which with a relatively stable excited singlet state may undergo transition to a metastable triplet state and sometime thereafter returns to the ground state, usually by emission of an ultraviolet or visible light photon. This is known as phosphorescence emission, and the process of crossing from a singlet state means no unpaired electron to a triplet state means two unpaired electron is termed as intersystem crossing. Now we have seen molecular structure and fluorescence. It is observed that all substances do not show fluorescence. Some exhibit fluorescence under suitable conditions of excitation by themselves, while others show it only when converted into suitable fluorogenic moiety. Thus, there appears a certain requirement in molecular structure for exhibiting fluorogenic activity. A generalization is as under. First, fluorescence is shown by those molecules which have absorbency. Certain types of electrons present in the molecule show high absorbency value and hence fluorescence. Second, compounds with multiple double bond and conjugated bonds show fluorescence. A high degree of resonance stability is necessary. Any group or substituents that alters resonance stability affects fluorescence. In many aromatic and heterocyclic compounds, fluorescence is shown by the presence of certain substituted groups. These should be at least one or more electron donating groups such as ammonia hydroxide, methanol on the resonating nucleus. Fourth one is electron withdrawing groups like acidic, nitrous, ammonia, chlorine, bromine, iodine diminishes or destroys fluorescence. Thank you.